Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady. So in the next couple of sections, we're going to continue to talk about the scheduling algorithm. We will mainly focus on the short-term scheduling algorithm. Now, processes are different, and the processes behave differently. Now, some processes, once they are created, they're going to run for a long period of time without user intervention. Now, while some other processes, such as interactive processes, they will frequently, interact with the users by receiving commands and the data, and also frequently generate output. So, in section 3.2, we're going to talk about the scheduling of batch processes. A batch process performs a long-running and a generally repetitive task. It does not require any interventions from the users. So some of the processes like the weather prediction and also the scientific calculations, so they just need the input at the beginning, and they're going to continue to run until they complete the job and generate the output. Now, these are called batch processes. Now, the scheduling of the batch processes are relatively simple. Now, one of the scheduling algorithm is called Fifo. First in, first out. Sometimes Fifo is also known as FCFS, first come, first served. Now, the Fifo schedules the process strictly according to the process arrival time. Okay, so when two processes or multiple processes compete for the CPU, then the scheduling algorithm is going to simply check which process has the earliest arrival time and allocate the CPU to that process. So the earlier the arrival, the higher the priority. Now sometimes some multiple processes could have the same arrival time. Now what happens? What the scheduling algorithm is going to do? Now in this case, the arbitration rule can pick up the process at random, even though in practice it's unlikely that the two processes are going to exactly arrive at exactly the same time. But the arbitration rule is going to apply in such a case. Now, Fifo is non-preemptive, which means if a process is running in the CPU, another process comes, then there's no way that the other process can kick the current process out of a CPU. Now, let's take a look at the example for Fifo. Now, suppose we have three processes, process 1, P1, P2, and P3. Now, each process has its arrival time. Process 1 arrives at time 0, process 2 arrives at time 1, and the process 3 arrives at time 3. Now, each process has a total CPU time. Remember the parameters we talked about for the process. So process 1 going to run 6 time units, and process 2 going to be running like a 3 time units, and the process 3 is the shortest one. Okay, only run for 2 time units. Now, how can we, schedule the execution of these processes? Let me actually change the color. Okay. So let's say process 1 arrive at time 0, and the process 2 arrive at time 1. process 3 arrives at time 3. So when process 1 arrives, then process 1 is the only process running, right? So then process 1 gonna be running. It will get the CPU and then start to run. Now at the time 1, process 2 arrives. So process 2 arrives at this moment. Now, since based on the Fifo scheduling algorithm, process 1 going to continue to run because the total CPU time for process 1 is 6. So it will continue to run. Now, when process 1 runs at about time 3, process P3 arrives. P3 arrives at this time. But process 1 going to continue to run until process 1 complete its job at the time 6. Okay. Now there are two processes waiting for the CPU. Two processes competing for the CPU. Now, which process the scheduling algorithm going to pick? Now, based on Fifo, remember, or FCFS, then it will check the arrival time. So then process 2 going to be running because process 2 arrives earlier than process 3. And the process 2 going to run for 3 time units, right? And then process 3 going to get the CPU and run. It's pretty simple. Because Fifo is not preemptive. So once a process gets a CPU, the process is going to continue to run until the process terminates itself. Okay, so that's 5. Now, many times we have some criteria to measure the behavior of each of the algorithms. One of the approach people use is to measure the turnaround time. The turnaround time basically measures the arrival time between the arrival time and the time the process terminates. So for example, for process 1, the arrival time is here, right? Time 0. And at the time 6, the process 1 terminates. So the turnaround time for P1 should be the difference between the time it terminates, which is 6, and also the arrival time, which is 0. So P1 has turnaround time 6. Now what about P2? P2, terminates at the 9, time 9, but P2 actually arrived at the time 1. So the turnaround time going to be 8. So that's the turnaround time, right? And then what about P3? P3 arrived at this moment at the time 3 and complete the job at the time 11. So the turnaround time going to be 11 minus 3. So it's also 8. So that's the turnaround time. Now, typically we use the turnaround time to measure the performance of each process in this particular algorithm. Now, basically to evaluate the algorithm itself, we normally use the average turnaround time. So that's the ATT. Now, average turnaround time is just add ATT for this FIFO. In this particular case, it is the 6 plus 8 plus 8. So the turnaround time for each process and divided by the number of process, which is 3. So what's the average turnaround time? It's let's see, 8. Yeah, that's the average turnaround time. Let's actually check it out. So 16, it's 22 divided by 3, 7. Yeah, 733. So that's the average turnaround time. Now sometimes we measure the performance for the algorithm using the average waiting time. The waiting time is kind of different. It just measures that the time when the process arrives and at the time when the process gets the CPU. Okay. So waiting time. So for example, the waiting time for P1. So P1 arrives at the time 0. And it gets the CPU immediately because P1 is the only process. So then the waiting time for P1 is 0, right? So it actually arrives at the time 0, but it gets the CPU at the time 0. So P1 doesn't wait for any time. Now what about P2? The time when P2 gets the CPU is 6, right? So P2 gets the CPU. And so it's a 6. Now the time when P2 arrives, it's 2. It's 1 actually. It's a T1. So that's the waiting time for P2. So which is 5. And the waiting time for P3 gets the CPU at the time 9, and P3 arrives at the time 3. So P3 waited for 6. Okay. So now we have an average waiting time. For the process, or for the algorithm. So that's the AWT, that's 0 plus 5 plus 6 divided by 3. So let's see what's the number. It's 11 divided by 3. Okay, so it's a 3.67. So typically we measure the performance of the process and the algorithm using these two measurements: average turnaround time or average waiting time. Either one going to work. Okay. Now FIFO is probably the simplest scheduling algorithm for batch processes. That's the bigger advantage. However, FIFO has its own problem. Now what's the problem? Now let's look at the example again. Take a look at the example again. So in this case, I just switched order of process 1 to 3. So now, in this case, process 3 arrives at the time 0. And the process 1 arrives at time 3. Okay. Now, what difference does it make? Let's take a look. Remember, process 1 has the longest total CPU time. Okay. And the process 3 has the shortest total CPU time. So now, if we let the process with shortest CPU time arrive first, and the process with the longest total CPU time arrives last. Now, what difference does it make? What's the performance? What's the performance change for the algorithm? So let's take a look at this again. So in this case, when process 1 arrives, process 3 arrives, right? Because process 3 arrived at the time 0. Process 3 is the only process. So you're going to take the CPU, run, and at the time 1, process 2 arrives, right? But process 3 is going to continue to run because it's a FIFO. It's non-preemptive. Now at the time 2, when process 3 finishes the job, process 2 gets the CPU and then start to run. And then at the time 3, process 1 arrives, right? Process 1 arrives. But process 2 continue to run until process 2 completes the job. So the total CPU time is 3 time units. Okay, and then process 1 get the CPU and then run to the very end. Okay, so now let's take a look at the diagram. So let's take a look at turnaround time for each process. So the turnaround time for process 1 is, let's take a look at the turnaround time for process 3 first, because then process 3 arrive at the time 0 and finish the job at the time 2. So process 3 is 2 times minus 0, that's 2. And process 2 arrives at here and terminate at the 5. Okay, so it's 5 minus 1, arrive at the time 1, right? So it's 4. And process 1 arrives at time 3, but finish at time 11. Still 8. So what's the ATT, the average turnaround time? So that's 2 plus 4 plus 8 divided by 3. So you can easily see it's much smaller than this. So it's 14 divided by 3. It's about 4.67. That's the average turnaround time. Now let's take a look at the waiting time. For each process. Process 3 doesn't wait, right? When process 3 arrives, it gets a CPU immediately. And the process 2, so arrive at time 1, gets a CPU at the time 2. So it's a 2 times minus 1, that's 1. And the process 1 arrive at the time 3 and it gets a CPU at the time 5. 2. So the average waiting time is 0 plus 1 plus 2 divided by 3. So that's 1. Do you still remember the average turnaround time in the previous case and also average waiting time in the previous case? Now this is much improved, right? Now, why it's dramatically improved? It's the same algorithm. Now the only difference is that instead of letting the process with the longest total CPU time run first, we let the process with shortest total CPU time run first. Okay, that's a difference. Now this actually somehow makes sense in our real life, right? So if you shop in the supermarket, now we have 2 people or 3 people. Now one person just carry a long shopping list in a big shopping cart, and the other one just carry a couple of beers. It's just, a small shopping list. Now, what's the feeling for each shopper. Now, if the first person with long shopping carts arrive first, it can actually take about 5 minutes to check out all the, the food or all the products. And the second guy with a very small shopping list has to wait for 5 minutes, right? So now let's turn around. If the guys with the actually small shopping list arrive first, and the checkout only takes about like 15 seconds, and then just leave, and the second guy with the long shopping list arrives, and it may take 5 minutes to check out. So now in that case, both people are kind of happy, right? In the first case, the second guy is definitely not happy because I actually make a small purchase, but I have to wait for 5 minutes for the previous guy to finish, right? So that's the problem with the Fifo. Okay. So now we have seen that the Fifo has a problem, because in case when a processor with long CPU time arrives before the processor with a short CPU time, then the average turnaround time or average waiting time can be very big, which is a bad thing, right? So now people just think about how can we avoid this kind of situation. So then the second algorithm, the shortest job first algorithm, was introduced. Now, the shortest job first algorithm, also known as the shortest job next, basically schedules the processes according to the total CPU time requirements. Okay. So the SJF use the parameter, the total CPU time, as the criteria to select the next process. So here's a rule. The shorter the required CPU time, the higher the priority. Okay. So if multiple processes have the same CPU time requirement, then the arbitration rule can select the process based on the arrival time. Okay, so we can do that, even though it's unlikely in the real scenario. So now, shortest job first actually has two versions. One is the non-preemptive version. The other one is preemptive version. So let's take a look at the shortest job first, which is non-preemptive version, because the shortest job first with a preemptive version probably has a different name. We use a different name for it. Okay. Now let's use the same example that we used in the previous slide. Now we continue to talk about these three processes, process 1, 2, and 3. Now the arrival time is 0 for process 1, the total CPU time is 6. Then for P2, arrival time is 1, total CPU time is 3. And for P3, the arrival time is 3, the total CPU time is 2. Now it's the same example as the first actually example used for the Fifo. Now remember, now we use the SJF scheduling algorithm, not the Fifo anymore. So again, when P1 arrives at the time 0, so P1 gets the CPU immediately, right? Because there's no other process at this moment. So now P2 arrives at time 1. Now P1 going to continue to execute. Remember, this is actually non-preemptive. So the operating system cannot kick the P1 out, simply because P1 has a long CPU time. So we're going to continue to run P1 and until P1 finish at time 6. So now, when P1 completes the job, now how many processes are waiting for the CPU? You know, P2 arrived at time 1. P3 arrived at the time 3, right? Now, if we use Fifo, then the scheduling algorithm is going to pick P2 because P2 arrives before P3, right? But now remember, this is shortest job first. So then the scheduling algorithm is going to check the total CPU time for P2 and P3 and find out the P3 has the shortest total CPU time, even though P3 arrives after P2. So P3 will be selected. And then P2. So P3 will run before P2. Now, what difference does this make? Unfortunately, P1 still, run first, and P1 has to finish before P2 and P3 can actually kick in. So let's take a look at the ATT. So first look at the TT, the turnaround time for each process. Now P1 is still 6, right? So it arrives at time 0 and finish at time 6. So it's a 6 minus 0, so it's 6. Now P2, so P2 arrive at the time 1, but P2 finish at 11, right? So it's 11 minus 1. That's 10. And P3 arrives at time 3, but finish at time 8. So it's 8 minus 3. So it's 5. So the ATT, the average turnaround time, is 6 plus 10 plus 5 divided by 3. Now what's the value? It's 7. Now remember, what's the average turnaround time for the Fifo? If you still remember, it was 7.33, I believe. So this is actually a slight improvement over the Fifo. Not big improvement, right? Why? Because P1 is still the biggest process and it's still actually finished before every other processes. Now let's take a look at the let's say the waiting time for each process. P1, let's say the waiting time is 0, right? P1 arrives at the time 0 and get the CPU at the time 0, and the P2 arrives at the time 1 and get the CPU at the time 8, right? So it's 8 minus 1, that's the waiting time. So 8 minus 1, that's 7. And the P3 arrives at time 3, but get the CPU at the time 6. So it's a 6 minus 3, that's 3. So what's the average waiting time? So it's a 0 plus 7 plus 3 divided by 3. So that's okay. Now the average waiting time is actually also improved over the Fifo. Now in general, in exactly the same scenario, the shortest job first will always beat the Fifo. That's for sure. Now we actually see that the shortest job first improves the performance, both in terms of the average turnaround time and average waiting time. But it seems like the improvement is still not so good, right? Now the main reason is because we still have the process with the longest CPU time finish the job first before the other two, process with a short CPU time. So how can we avoid this? So now here on the right, we basically summarize these diagram that we just drawn in the previous slide. Now, how can we improve this? Now, the problem is that when P1 arrives, P1 with a long CPU time, CPU burst, is the only process in the system. So it will take the CPU, but when P2 arrives at the time 1, so now we find out P2 has only 3 time units for the CPU time. It only takes 3 time units. Now, what about P1? P1 has completed 1 time unit, but the CPU time is 6 time units. So there are still 5 time units left. Now compare with 3. So in that case, so the remaining time for process 1 is still larger than the total CPU time for P2. So now, what about if we replace the P1, just kick P1 out of the CPU and replace the, P2. So let the P2 take the CPU. Do you think we're going to improve the performance? The guess is yes. So now, in this case, it's still the shortest job first, but now we use the preemptive version. So, and we call these the shortest remaining time algorithm, SRT algorithm. So SRT is a kind of shortest job first, but it's a preemptive version. So the SRT schedules the processes according to the remaining CPU time needed to complete the work. So when a new process is created, it will the scheduling algorithm going to compare the CPU time for the new process with the remaining CPU time, for the process in the CPU. The process is currently running. So you just compare the remaining time with the new process, and whoever is shorter will get the CPU. So that's the SRT scheduling algorithm. So in that case, the shorter the remaining CPU time, the higher the process. Okay. Again, the arbitration rule applies if multiple processes have the same remaining time. Okay. So from this perspective, SRT is the preemptive version of SJF or SJN, the shortest job first or shortest job next. So whatever you call it. Okay. Now, so let's take a look at the example again. Now this time we use exactly the same processes, P1, P2, and P3. P1 arrives at time 0, P2 arrives at time 1, and P3 arrives at time 3. Okay. So remember, we just did this for Fifo and also for SJF. But let's take a look at this example for SRT. So when P1 arrives, now P1 gets the CPU time. Why? Because P1 is the only process in the system, right? P2 and P3 hasn't arrived yet. So now P1 executed for about 1 time unit, and then P2 arrives. So then the SRT scheduling algorithm gonna be kicked in and check, which one has the shorter remaining time. Okay, so then we calculate that the P1 is 6. 6 is the total CPU time for P1, but it's already executed for 1 time unit. So there's a 5 remaining CPU time left. Now what about P2? P2 has 3, right? So 5 compared with P3, so P2 gets the CPU. P1 is kicked out. Okay. Now P2 gonna continue to run and until at the time 3. Now P3 arrives. So now in this case, we have 3 processes, P1, P2, and P3. Now what's the remaining time for P1? It's 5, right? Because P1 was kicked out at the time 1. So it's still, the remaining time for P1 is still 5. Now what's the remaining time for P2? P2 has executed for 2 time units. So total CPU time is 3 for P2, but it's already, P2 has executed for 2 time units. So there's only 1 remaining. And P1 has 5 remaining, right? And P3 has 2 remaining. So still, 1 is the smallest. So P2 continue to execute. Now at the time 4, P2 actually complete the job. Okay. So then you have 2 processes remaining, P1 and P3. Now remaining time for P1 is 5, remaining time for P3 is 2. So P3 gets a CPU and executed for 2 time units. 2 time units. Okay. And then P2 complete the job, and then there's only 1 process, in the system. That's P1. So then P1 gets the CPU time and complete the job. Okay, here, let me actually draw this table so we can get a better understanding of these SRT scheduling. So let's say there's a P1, P2, P3. So now at the time 0, that's the time. Okay. Now P1 arrives, right? So then what's the remaining total CPU time? It's 6, right? Because P1 hasn't started yet. So the total CPU time is the remaining CPU time. And the P2 and the P3 is not applicable. Okay, it's not there yet. Now at the time 1, when P2 arrives, so then we're gonna, the scheduling algorithm gonna check the remaining time again for all the processes in the system. Now, what's the remaining time for P1? Now, after 1 time unit, P1 has 5 remaining time. Now, P2 has 3 remaining time. P3 is not there yet. Okay. So now here P1 is selected because P1 is the only one. Now here P2 is selected, right? And now the next time is 3. When P3 enter the the ready queue and fight for the CPU. Now what's the remaining time for P3? It's 2, right? Now remaining time for P1, it's still 5 because P1 was kicked out at the time 1, and it's still it's still 5. Now P2 actually enter at the time 1, it was 3, and then after 2 time units, P2 has 1 remaining, right? 1 time unit remaining. So which one will be selected at the time 3? Still P1. So that's why P2 continues. And then at the time 4, P2 complete the job. Okay. Now we only have 2 processes left, P1 and the P3. So then we compare P1 and the P3, and the P3, is selected. So then P3 has, 2 total CPU time. So P3 complete job at the time 6. So P2 already completed. So now there's only 1 process in the system. So P1 will be selected. And then at the 11, P1 also finished the job. So all processes complete the job. Okay. So now let's take a look at the performance. Again, let's talk about the turnaround time for P1. So P1 arrives at the time 0. Now remember, P1 has two blocks. It's split, right? There's the first part and the second part. So P1 arrives at time 0 and was kicked out at time 1. So the first block, the turnaround time is 1. Now the second part, so it was kicked out at 1 and eventually finished at 11. So for the second one, the turnaround time is 11 minus 1, the time 1 it was removed from CPU. So it's 11, still 11. Now P2 actually complete job at the 4, arrive at 1, right? So it's 3. And the P3 complete job at the 6. Actually P3 arrive at the time 3. So it's also 3. Okay, so now the average turnaround time going to be 11 plus 3 plus 3 divided by 3. So what is this? It is the so that's 17 divided by 3. So okay, it's 5.67. It's 5.66666. They're going to continue with that. So I just, truncate to 5.67. Okay. Now let's take a look at the waiting time. Now P1 again, P1 has two parts. The first part, it arrives at the time 0 and get the CPU at the time 0. So the waiting time is actually 0, right? It did not wait. Now for the second part, okay, so it was kicked out at the time 1 and then regained the CPU at the time 6. So the second part is 6 minus 1. So it just quit the CPU and then regain the CPU. So it's 6 minus 1, so it's 5. And the P2 is, let's see, P2 arrived at time 1, right? And immediately get the CPU at time 1. So P2, the waiting time for P2 is 0. That's good, right? P3 arrive at time 3, but waited for 1 time unit after P2 complete. Get the CPU at time 4. So get the CPU at time 4 and arrive at time 3. So P3 waited only 1 time unit. So let's take a look at the average waiting time. So it's a 5 plus 0 plus 1 divided by 3. That's 2. It's pretty good, right? So if we compare the SRT and the SJF, so SRT has a better performance than SJF. Okay. Okay, so far we discussed 3 algorithms, 3 scheduling algorithms. One is Fifo, the SJF, and SRT. Now, we find out the Fifo is probably the worst, but it's the simplest one. Now, SRT is probably the best in terms of performance we measured. We measure the ATT, the average turnaround time, and also measure the average waiting time. Okay. So now when we design the scheduling algorithm, the main objective in scheduling batch processes is to maximize the number of processes completed per unit of time. Okay. So we try to make sure in a fixed period of time we get more processes done. The order of in which processes are executed cannot reduce the total CPU times. Now let's take a look at all the diagrams for the diagrams for all these different algorithms. So now we know that the process 1 takes 6 CPU time, process 2 takes 3, and process 3 takes 2. So the total is 6 plus 3 plus 2, it's 11. So it doesn't matter which scheduling algorithm we use. In order to complete all the processes, we have to actually run for 11 time unit. You can see this. The complete time is 11, complete time is 11, complete time is 11. The only difference is, each algorithm going to allocate the CPU to a different process at a different time. So it's the order in which process are executed cannot reduce the total CPU times of the individual process, but can reduce the waiting time. Okay, like a waiting turnaround time and a waiting time. So we measure the turnaround time, right? And we also measure the average turnaround time for each algorithm. Now the other actually measurement we use is the average waiting time. In either way, it's just a different measurement, but it will get the same conclusion. The short SRT is the best in terms of the performance. Okay. Now, the waiting time is not the only criteria to measure whether an algorithm is good or not. Now, there's another important objective for the scheduling algorithm is to guarantee fairness. Okay. So now, if we use the shortest job first, for example, now it's good in terms of performance, in terms of waiting time, right? Or the turnaround time. It's all good. It's probably better than the Fifo in any circumstance. However, the shortest job first may have the issue of fairness. Now, for example, if one of the process has the longest, extremely long CPU time, and then during the executions, and some processes actually generated, some process finish job, and the other processes are created. Now, it's possible that after a very long period of time, all the process comes and goes, but this particular long process never get a chance to get the CPU. So that's called starvation. Okay, starvation is the indefinite postponement of a process, while other processes are allowed to proceed. So both SJF and SRT can lead to starvation. There's a possibility for this. Okay, so here's a summary for all the different scheduling algorithms. Now we basically measure the performance using the ATT, the average turnaround time. So now the first one is basically measures the 3 processes and the arrival time for each of the processes. Okay, and the second one using the Fifo, and I'm sorry, the first one used the Fifo, and the second one used the SJF, and the last one was use SRT. So now we actually discussed all these. This is just a summary. So you can check the average turnaround time for each of the case. Now the SJF has a slight improvement over the Fifo, but SRT has improved a lot. So you can see this. Okay, in this slide, we're going to talk about how to estimate the total CPU time. Now, remember that SJF, the shortest job first scheduling algorithm, determines the priority of the process based on the total CPU time. Now, the shorter the total CPU time, the higher the priority. So now, once a process is created, okay, so it's in a new state, and if the long-term scheduling algorithm decide that they're going to move this process into the ready list, right? Okay, so now the process is in the ready list, fighting for the CPU. Now, if the shortest job first scheduling algorithm is used, then the CPU going to decide, the scheduling algorithm going to check each of the processes and pick the one with the shortest total CPU time, right? That's what the SJF algorithm is designed for. Now, the question is, all the CPUs are in the ready list, right? So how does the scheduling algorithm know that which process has the shortest CPU burst? That's a question. Now, after the process completed execution, then you know, oh, this process took about 10 minutes or 10 seconds, then we know. But before that the process start to run, how do you know which one has the shortest CPU time? So that's a problem, right? So now in reality, the shortest job first cannot use the true total CPU time to decide which one will be selected. So the shortest job first algorithm going to actually use the estimated total CPU time for each process, and the process with the shortest estimated total CPU time gets the CPU. So it's estimated CPU time, total CPU time. So now, initially, when a process is enter the ready list and try to fight, and based on the scheduling algorithm, you're going to assign an estimated total CPU time. What is this? Sometimes they're going to randomly assign a number. For example, every new process is going to assign the total CPU time like a 10 second. So then, based on this number, the process start to compete with the other process. So it start to run. And then after it stop the execution, and then the operating system is going to measure what's the actual total CPU time. So in this case, there are two data. One is the estimated CPU time, okay, and then the other one is observed CPU time. The decision is made by the estimated CPU time. We use the S, okay, so or sometimes we call it predicted. We predicted CPU time. Now that's the observed, so that's the actual CPU time. And then, so now we got predicted CPU time and observed CPU time. That's the actual CPU time. And then the process is actually either in the ready list or in the blocked state, and suddenly it's back again and in the ready list and selected for execution. Now, then this time, before the process fight for the CPU, you're gonna use another estimated CPU time, the predicted CPU time again. Now, how do you calculate the predicted CPU time? That's a very important issues here. So now, the more the process actually acquire the CPU and execute in the CPU, the more we know about this process. and that the better we can predict the CPU time. Okay, so here is the formula we use. Suppose that the process actually run like first time you have a predict the CPU time S1, and then we have actual CPU time T1, and then we use some formula to calculate next predicted CPU time for next run, right? And then after the process complete the job, and then we got T2, the observed CPU time, the actual CPU time. And then again, we need to do the predict the CPU time before the process acquire the CPU again, and then get the CPU based on the predict the CPU time. So we calculate the S3 based on the previous information we got, and then after it finished, you got the actual CPU time or observed CPU time. So we keep actually doing this. Okay, hopefully each time we complete if the process completes the execution, then you have better idea to predict the next CPU time. Okay. Now, the most common approach uses exponential average, which combines the last estimated total CPU time. Okay. So each time we have predicted CPU time, like the first time, and then you actually got the actual CPU time, and then we use this data to predict the next one, and then we got the next actual time, and then predict the next one, and you got the actual CPU time, and you keep predicting, and you keep getting the actual CPU time. So here, this is the formula widely used in many scheduling algorithms. So let's say to predict the next total CPU time Sn plus 1. Suppose the process has arrived n times and departure n times, so executed n times, and this is n plus 1 times. Okay, so then it will use the previous observed CPU time Tn plus the previous predicted time, and then we use a weight. It's called alpha, and then the other one is called minus alpha. That's the weight, and the alpha, the weight is selected between 0 and 1. Okay. So the value alpha is the weight. Alpha controls the relative weight of the last observation Tn, and versus the history of past predictions. Okay, now you can pick, for example, if you pick alpha equals 0, so that means Sn plus 1 equals, if alpha is 0, then you got Sn n, right? So that means the next predicted time for next predicted time, the CPU time, we're going to use the previous one. Now, if alpha is 1, then Sn plus 1 going to be, if alpha is 1, going to be Tn, because second one, 1 minus 1 is 0. So the next predicted time going to be the Tn. So that means the previous observed time going to be used to predict next CPU burst. Now, these are two extreme cases. Now, many times we probably use alpha equals 1.5. So that means Sn plus 1 going to be alpha going to be 1/2. 1 minus alpha is also 1/2. So we're basically going to use the average of the previous observed time and the previous predicted time. So this is the value we're going to use to predict the next CPU burst. So that's the way we use. Okay. Okay, here's an example. So then this is the number of CPU burst. Okay. So initially, we use the predicted CPU time SI. So initially we predicted that the CPU time is going to be 10. Okay. And then we find out the actual CPU time is 6. So predict 10, and actually the process is actually after execution of the process, we've observed that the actual CPU time was total CPU time was 6. Okay, so the prediction was wrong. It's not really accurate. Now, however, we're going to use these two data to predict the next CPU burst. So again, so the next CPU burst S1 going to be used. Okay, it's 8. Now, how can we get the 8? So here we use the formula Sm plus 1 equals, now we use 1/2 as alpha. So then it's the formula going to be like this, right? So when n equals 0, that's the n. So we're going to calculate the next predicted time going to be the previous observed time is 6, right? And the previous predicted time is 10, and divided by 2, so we got 8. Okay, so that's the value S1 we're going to use. Now, so we use this number as predicted total CPU time and use the number to fight with the other processes. Now, if 8 is the shortest estimated total CPU time, then this process will get the CPU, right? Now, again, suppose we use SJF. Okay, so now once the process gets the CPU and execute in the CPU, and then we actually observed that the process only used CPU for 4, say 4 seconds. Okay, or if it's any other time units, then it's just a 4 time unit, right? So the prediction is wrong again. So the actual CPU time is actually shorter than 8. So that's fine. Then we continue to do the prediction. So we're going to use the previous, predict the CPU time and the previous observed the CPU time to predict the next one. So now n equals 1. So now we just try to predict S2. So what's the predicted CPU time? It's 8, right? The observed CPU time is 4. And then we just calculate, we got a 6. So the 6 becomes the next predicted CPU time. And then we actually run this, the SJF, and use 6 as the predicted CPU time and fight with the other processes. And we find, now once the 6 becomes the smallest predicted total CPU time, then the process gets the CPU. And then actually, after the execution, we observed that the CPU time was actually, total CPU time was actually 6. So that's the first successful prediction, right? So the prediction is correct. So now what we're going to do for the next prediction. So if we want to predict the next CPU time, then we use the average again. So the observed CPU time 6, predict the CPU time 6, and then we do the average. So we got a 6 again. Now that makes sense, right? Because the predicted CPU time is 6 and the actual CPU time is also 6. So that means, looks like our prediction is perfect. So we're going to keep using this same number. Okay. And then that's the next one, S3. Again, after the CPU execute this process in the next CPU run, then we find the observed CPU time was 4. So that then we're going to use this in the next prediction. So the observed is 4, predicted was 6. Okay, we use this 2 data, and we got a 5. So because the observed CPU time was 4, which is smaller than the predicted CPU time, so we adjust the predicted number to make it smaller. Okay, so we just keep doing that way. Okay, now this diagram basically gave you the idea, between the actual CPU burst and predicted CPU burst. Okay, so that's the actual one. So the actual one is 6, and the second one is 4, and then we got a 6 again, and then we got a 4 again, and then the next one there's a jump. Okay, the actual CPU actually jumped to 13, and stays in 13. Now here's the predicted one. So the first we predicted 10 because we don't have any prior information. So we maybe randomly pick 10. And then after the first actually observe the CPU time, we just make a next prediction, which is 8. Okay, so that's the, let's say that's S0, that's S1. And then the next prediction was 6, S2. And then S3 is 6. Okay, yeah, that's S3. And then the next one is 5, because the actual CPU time is smaller than the predicted value. So it's, I'm sorry, it's 4. And then the next one is, what is it? It's S4 is 5. I'm sorry. Yeah, it's 5. And then the S5 is 9. It's 9. So yeah, that's this. So it's keep going up. So now you can see that the predicted CPU time and the actual CPU time did not match. It matches only in certain places, but it basically followed the trend, right? So if the actual CPU burst is, keep the same as a constant, stays at the 13, eventually the predicted CPU time going to be approaching 13. So we use the predicted CPU time as the estimate as the actual total CPU time, and use the predicted CPU time in the shortest job first to decide which process should be running. Okay, so that's what we do in the real actual operating system. Okay, so let's wrap up the section 3.2 by summarize the formula used to predict the total CPU time. Remember, the formula is like this. The next predicted time is alpha times the observed time, the previous observed time, plus 1 minus alpha of the previous predicted CPU time. Okay. Now, when you look at this formula, then you will find out that with a large value of alpha, if alpha is very large, like on the left diagram, so the largest alpha you can take is 1. So 0.8 is kind of large. So that means the predicted value, each prediction is based mostly on the last observed value. Okay, so this first part is going to play an important role in the next predicted value. Now, of course, the advantage of this is that the predictions adapt quickly to any change. So if the actual, CPU running time is big, then predict value change to a big one. And if the CPU actually running time is small, then we predicted that the next CPU burst is going to be small. So So look at this diagram. The blue color is observed CPU burst time, and the orange color is the predicted. So the predicted is pretty much follow the previous observed, because there's always a delay for the predicted value, right? Because predicted CPU burst time, CPU time is based on the previous, observed CPU time. So there's a delay, but it's kind of close. Okay. Now, what's the problem with this? Now, in most cases, if there's a spike, like this case, and then the predicted value also has a spike, which is not quite good in terms of the process execution. So now, on the other hand, with a small value of alpha, so if alpha is small, so that means this first part is smaller and the second part becomes bigger. So now, in this case, it's each prediction is based on mostly on the weighted history of past prediction. Now, the advantage is that the predictions ignore outliers but adapt more slowly to the change. So it's a little bit stable, So in that case, the spike in the observed CPU burst plays a small role in the predicted value. So any isolated, CPU burst will be probably ignored in the predicted CPU time, which is also good from some perspective. Okay, so that's pretty much all for the section 3.2. Thank you.